Java on smartcard is zeg maar niet permanent virtual machines. Altijd, zeg maar, als je de kaart eruit haalt, die blijven in de staat waarin ze in staan. Ja, precies. Ja. Is dat micro edition of is dat nog gelijk? Ja,
dat is van Java kaart.
Ja.
Die bestond voor mij. Die stond er voor jou mee.
Ja, het is geloof ik zelfs geen int hè, in die Java. Nee, precies. Oké, beste mensen, welkom in de presentatie van Eduard de Jong over Java card technologie. Een onderwerp waar ik niet zo veel van af weet, maar ik heb intussen begrepen dat je zelfs geen... Oh, oké, sorry. We start again. Please welcome people to this talk of Java card technology. It's a subject I don't know very much about, but Eduard de Jong is going to tell you everything about it. Eduard.
I have my mic here. So let's begin by telling who is present here. I started in smart cards way back in 1990 when I joined David Schaum building a smart card system for payments, anonymous, and all kind of advanced cryptography. After 2 years, I had enough of that and did my own stuff. And in the meantime, I came in contact with the hacking world in Galactic Hacker Party. Then I moved to California, where I started a company together with some French guys, and I made a smart card software to run an operating system, and that became Java Card. And so the last years until 2008, I worked at Sun Microsystems, trying to convince the world about the beauty of Java Card, which I can share with you right now. So first, I need to know a little bit about where you are and how detailed I can get going. Have anybody here of you done anything with Java? Oh, that's quite a fair amount. Good. That makes life easy a bit. Let me see. Does it do it work? Yes. Smart cards. Oh, good. Oh, that makes life a bit easier too. That's a small amount, good. I have at least some people who don't know I can teach something, good. Well, this one is, we'll skip this one. So, 4 parts in my talk. First we talk about smart cards, just for those who haven't been aware of how things are going. About the Java card technology in its own right, then what can you do with smart cards and with Java card, how can you work with them? And then finally, I talk about security, which is always an interesting topic to look at, especially in the context of trying to use it in your own way. Smart cards, what are they? What are they made of? And what can we do with it? Let's see. It's a plastic card, usually in the card of a form of an ID, but most cases there's a piece cut out and you get the ID 0 format, which is going into the GSM phones. It's a 16-bit CPU nowadays, has a fair amount of ROM, some E-square, and some RAM. When we started in 1990, it was quite different. It was 8-bit CPU, 128 bytes of RAM, 3K of E-square, and about 8 kilobytes of ROM. That was the kind of operating systems that triggered development of very special software that would run and be programmable, etc. I/O. Most cards are still using contacts. Some cards don't use contacts. When they are contacts, there are 8 contacts. 5 of them are used. At least 5 of them are used in the normal way. If you have a USB card, only 2 are used. The 2 which are not used in the other case. And if you have an NFC card, which is sometimes in modern GSM phones, the 5th pen is also used as well. The contactless cards also exist, are claimed to be in the RFID world. Things that smart cards are RFID tokens, but smart cards existed way before RFID existed. The communication with a card is always based on a particular protocol, which is called APD protocol, and I will talk about it a bit later. But it's particular to smart cards, whether you use contacts or contactless, or whether you use USB or not. You always talk with the card using that particular smart card protocol. Smart cards are special. They have secured silicon. And the silicon has been attacked and has been strengthened, and at that point in time we have basically no database that you can see and probe. It's completely down deep in the silicon. Memory is encrypted, the data path from memory to the CPU is encrypted, and only decryption happens just before the data is being processed in the CPU or in the crypto hardware, which is also there. There are all kinds of sensors. If you try to shine light at it, if you try to do radiation, if you try to remove the passivation layer and try to make contact with the contacts, all those things will be detected. Of course, all sensors can be defeated, but it's just a battle between those who try to break in and those who protect. And then, of course, there is a lot of obfuscation happening on what is on to prevent you from gleaning anything from what the processor is doing in speed or in current used. And it contains crypto hardware. It contains hardware to doing RSA computations. Most new ones have elliptic curve hardware. They have DES hardware always. Some have DA hardware, and there is always a random number generator nowadays. This makes this chip very good for doing cryptography and security. It is like a much smaller version of the hardware security model which you find in the server farms that use SSL. Smart cards are, last year, I looked it up, it's on the website somewhere. There's memory cards which are stupid. They have no programmable CPU. They have some logic usually. This is the MIFARE Classic is the main example, and the major part of this 900 million cards are MIFARE Classic cards being used in public transit or in telephone cards. All the cards which are programmable, the CPU cards, 3 billion cards went out into the GSM market last year. And then there's a whole lot in governments, that's citizen ID cards and cards for the employees of government. The EMV cards, the debit and credit cards, which you can use all over the world, are also light fraction. This is about 10 times more, or 20 times more than the number of CPUs shipped for desktop computers and laptops. It's about the same amount of processors shipped as for all the embedded processors in the world, and it's about the same amount as the cores that are embedded in processors like handsets. So smart card chips are really a very big business for silicon manufacturers. Although it's big in volume, it's not big in dollars, because the price on most smart cards is very low. At volume, you pay $1.50 or $2 for a smart card. The higher smart cards which now are available with 32-bit processors and much larger memory are much more expensive. So the big volume is still in the low-cost cards. And smart cards are basically used for GSM. That's the bulk of it. Passport, a very nice application where lots of things have been done about trying to use them and make them useful. It's very hard, especially since IKEA, who started passports, didn't really understand smart card technology and tried to just plug all the things that had readable for humans and readable for machines into the remote readable or RF readable stuff with all the security risks and break-ins that it involves. For EMV, the banks, the main reason to use cards is that they want to verify pins at the point of sale or the point of service, and security is very important there. But in GSM, security was nice, but the reason they wanted it is that smart cards enable operators to work on handsets that are manufactured by independent companies, and they share the customer in a way. So this concludes my introduction to smart cards, and we can now move on to Java card and see what is special there. The reason we started Java card was to make it easy to write code for processors that run on smart cards. At that time when we started, which is in '96, there was no way of programming cards except writing assembly. And some C compilers were emerging, but you basically wrote assembly code and had to handcraft everything you did. And every application required a new mask. And masking time was 20 months or so to get a new version of the software in the smart card and test it. So having software that could be loaded in non-volatile memory and programmed and tested as you write normal code and using object-oriented languages to express the things you want was why we started Java Card. We also want to make sure that if you have one application on the card that works some keys and some data, it is separated from anything else on the card. And that's the multi-application card. There are only a few of them still exist, but that was the intention when we started. And of course, since you write in a high-level language, you can actually communicate with the card in basically the same way you communicate with any other processor. And that also would make it easier to use smart cards. Let me see where we are. So Java Card is starts with Java programs. And you compile a Java program. The animation should work. The Java you use is not the full Java. It is a subset. And we'll talk about the things that are not in Java later. The compiler is just a standard compiler. And the class file is a standard class file. But of course, since you don't use all the, since you cannot use all the bytecodes because some things won't be accepted by the card. And therefore, in general, because you programmed correctly, you will have only a subset of the bytecodes in your class file. Then you take the class file and it is processed in your development environment in something that's called a converter nowadays. This slide, by the way, I found in the presentation I gave in 2000 for the NSA when we tried to convince them that Java Card was good for the military identity card. So I thought this was a proper occasion to show it again. The post-processor, the converter, takes the cap file, more cap files for all the classes you have made, and class files and creates them into a cap file, which is a loadable file that can actually be loaded into the card. And in the card, you'll find a library of classes which are specified also as Java language, but they're implemented in the card as a reference. And then you have the virtual machine, which is not a Java virtual machine, but it's a virtual machine that looks like Java virtual machine, and it is programmable through this whole path in Java language. The result is an API, a virtual machine, and some hardware facilities underneath it. Just another layered software architecture. The applets can be anything. They are separated. Usually you'll find an applet that is the manager applet that allows you to load code and that can install and manage the keys in other applets. So what is special for Java? The objects are very simple. There's no clone, there's no hash code, there's equals you can implement if you want. There is no system. There's a special GC system class which has some facilities that Java system class will bring. What is new, it has transactions. Every modification to an object that's stored in the non-volatile memory is always transacted. So you will always be sure that what you write, what you want to write is always written, and the VM only resumes when things are written. There's a special facility for creating larger combinations of writes into a persistent transaction, which has a rollback facility, and you can actually explicitly remove a change to your data by rolling back changes. And then there's the firewall, the separation between applications. This is not the same thing as the sandbox or model of security. It is a really virtual VM. When you are an application in Java Card, each application runs in its own virtual VM, although they share the heap and they share the stacks and all the things are basically separate when you are running in the firewall. There are ways to communicate through the firewall, but it's too complicated to go into right now. But you can exchange data between applications in different firewalls. So there's no longs, no floats, no doubles, no ints, no strings, no char, and there's no multidimensional arrays. It's pretty limited. The limitations came from the small size that we needed at the time. And still, if you look at RFID chips, they are still small, and Java Card is still very suitable for very small processors. There is a special runtime environment which has no garbage collection, no threads, no cloning, no dynamic class loading. All the class loading is done before you even load into the card in the converter, in the post-processor that takes all the class files and basically does all the loading and all the linking that happens beforehand. This technology goes back, way back, almost as old as the previous speaker about IBM. 1994 was the first version of the Java card technology. In 96, Schlumberger Technologies in Austin released a spec called Java card. But that didn't go anywhere. It had a brand name Java card, it had programmable in Java, but the runtime model was completely wrong. And the redone version, the second version in 97, was the one that was taken up in the market. GSM started doing it in 99, and in the end of 97, Sun Microsystems actually bought the company that I worked for, and Java card has been with Sun ever since. And last year, the third version has been released. We have only seen 3 changes in the specs, very minor changes. And in 2008, a third version was released, much larger footprint for much larger chips. It can connect, it can support an IP stack and all kind of other things that servers support. But as up to now, only very few companies have actually taken up. And the old specification will live on as a Java card classic or whatever brand Sun will stick onto it, but it will stay on and it'll be available for use. An application in Java card is built like any other application. You design code and debug and make sure it runs. Then you have to go through the converter. There are all kinds of end tasks that will integrate all this work for you. And then you have to go and find a card or find an emulator and load it on and make sure it actually works on the card. If you buy an IDE from a smart card vendor, you will get a set of blank cards which are open, and you can actually load them as if you are loading in a real card, except there's no protection on that load mechanism, so the cards are really open. That would be the only way to actually get real cards is you can actually real program in Java card, is to buy a development kit from a vendor. So finally we can show some real Java code. So we can, those who have been waiting for real Java, you can now look at. This is an applet, and there is a huge set of example applets available from the Sun website. And so there is a class. This is a purse applet, a prepaid card applet, and it extends applet, which is defined in the Java cards framework. And it has, and the main thing it does is handle incoming commands. And commands are APDUs called, and so we see here the method process APDU, which is the main method that will handle anything that the environment of the card throws at the card. And there is the conditional here which says, if you have a special format, the standard format, do something different. But in this case, if you want to have a special command, initialize transaction, and you do initialize transaction. So you will have a huge case statement here to test whatever is coming. This is not object-oriented programming, but it is programming of cards using Java. There have been attempts to make it better and more object-oriented, but the market never really liked it, so I was sitting there at Sun and tried to convince them to be more pure, but that didn't work out. Anyway, this is the basic of writing an applet for Java card. You just fill in the process method, define your commands, and in all those methods, you define all kind of methods, we take APDUs, and do whatever you need to do, and create a response and send it out to the world to work with. Oh, I don't know where we got there. Somehow, I got to the end. Oh, good, back. So, this was the end of Java. If there are any questions, you can raise your hand now and I will try to explain better. Otherwise, we can wait to the end. Now you have a Java card, you built some program in it. How does it go about to actually make use of that card? You have to communicate with the card. And the first thing you have to do is to get power to the card. It will tell you something. You can exchange messages. And you have to understand how the messages look like. And then you have to know what application there is, so you have to find your application first. The first thing a card does is send out an answer to reset. It's called ATR in the lingo of smart cards. It defines communication protocols, like the bit rate and some other things, timeouts and other. It also specifies the protocol to use, the low-level packet protocol. There are two protocols defined, and many attempts to define better protocols. T=0 has been defined in the late 80s. It was a protocol that could be implemented on even smaller processors than I just mentioned. T=1 was an attempt to do it, by the Germans, by the way, to do a much more rigorous OSI-compliant version of the protocol. Most cards now support both protocols, but all cards always support the T=0 protocol for the first few bytes they send out, and you can then negotiate with the protocol exchange protocol, the protocol you want. T=14 is the protocol that you want to do if you're hacking the card, because you can define anything you want. It means after you have specified T14, your card can switch to whatever protocol it likes, and you are on your own, and you can ignore any standards and do whatever you like. The speed possible with cards used to be about 256 kilobit. Nowadays, you can go up to 2 megabit in T0 or T1 protocols. So that's pretty fast for the cards. Most terminals, on the other hand, are either 9K6 or a bit faster. So if you buy a reader on the market, the speeds of the card are usually limited by what the reader will offer, which is usually very moderate. The ATR also has some other data. It has 32 bytes possible at maximum to tell about what is in the card. There's no standard for it. Some manufacturers put the name in there, put the version of the product, the size of the ROM or whatever. There's no prediction of what it is. There is some use of it in some software in the terminal, but it's not predictably to work. So there's no way to find out. The protocol that you use after the card is powered up is called APDU protocol, for Application Protocol Data Unit. It's defined in a standard. It's defined in the early 90s. It's been reworked in the 2005 edition of the standard. It's half duplex. The card waits, it gets a command, processes it, sends out the response, and waits for another command. The main thing is it just has a simple header. The first 2 bytes specify whether it's compliant to the standard, and if it is compliant, then the second byte actually tells you what kind of instruction it is giving. The other 2 bytes are parameters. Then you have a payload, and the payload used to be 256 byte maximum. Nowadays, some cards support the longer version, which is up to 65K. Of course, most cards don't have the memory to support 65K messages, so they have a way of indicating that they can accept 4K, 8K bytes of memory, depending how much RAM they have and what they want to do with it. If you not understand, if the first bit of the message you send is a 1, you basically can do what you want. You're still bound to the T=0 or T=1 protocol for the actual packet format, but how you interpret the rest of the byte is up to you. So if you specify T=14, and then you're on your own. If you specify T=1 or T=0, and you can still use whatever command format you like if you use the non-standard formats. In Java, since you can program what you want, there actually is a copy made of some of the standard facilities, which is the logical channels. If you use a standard command, you can specify 20 different possibilities, 20 simultaneous applications that can be active in the card. You can specify a logical channel. You can open and close those channels. And they are like virtual connections or ports on the IP connection. Very primitive, but it works. And most cards nowadays support at least 4 or always the full 20 logical channels. Java card supports logical channels also when you have proprietary commands, the non-standard ones, when you have the first bit set to 1. You can actually, in one range of bytes, you can actually indicate a logical channel. So you have a logical channel that's compatible with commands on the standard ones and the non-standard ones. If the card is one side There is a reader involved. It's contacts, which makes contact to the contacts and links to the USB port or the serial port of your host station, your terminal. PCSC is the common standard for use for that. It's a layered architecture which allows manufacturers of readers to plug in some plugin that talks to their reader. Some readers have a display or buttons, and then you can use those buttons and displays if you use their plugin. There's another layer which looks at the ATR and tries to determine what the card can do and brings the functionality of the card in that way. But most cards have meaningless ATR, so there is a transparent plugin which basically gives you the APDUs on a named socket, and you can talk APDUs to your card when you open that PCSC daemon. And all operating systems, Linux, most Linuxes have them, macOS has it. It's all based on the open source version of PCSC, which is the Musclecard project, and the PCSC there is called PCSC Lite. The PCSC consortium itself started way ago by Schlumberger and Microsoft, trying to bring cards to the Windows system, which really didn't work out that well, but other systems took it up, and now we're here. There is a Java version of the framework, the same age, started also in '95, being put into Java. It failed to be the only framework, and now it sits on top of PCSC. So if you write a program your things in Java, in the card and in the terminal, Open Card Framework is still available. There are some alternatives. There's an attempt then to make remote method invocation available on cards. It's a facility which exists, but it's very limited usefulness. There is another protocol layer defined in JSR 177, which looks like Open Card Framework, but is not exactly the same. So there's a choice of ways in Java to talk to cards. Once you know how to talk to a card, you have to find out what to talk to. And the thing you have to talk to is identified by 5 bytes at the minimum or 16 byte maximum, which is called the application identifier, the AID. And there's a command, a standard command defined in that ISO standard, which allows you to select the application. And in a Java card, if you select an application, that application is notified that it is going to be talking to the terminal by calling a method on the applet class. It's an abstract method, so if you don't implement it, you will not get notified. You will just receive commands. But if you implement it, you can then do some reorganizing, opening, copying some data from your non-volatile memory, from the E-square into your RAM, so that you can actually have access to it. Make sure all the constructions were closed properly the last time you were running, etc. So you make sure that you can actually accept commands. Once you have then selected the command, you're on your own. The application can do what it likes. Within the confines of the firewall and other security constraints, you can run cryptography, etc. But the first, yep? Yes, of course.
How do these logical channels then relate to this application identifier?
So there are 2 mechanisms defined for managing logical channels. So the question is, how do logical channels relate to the applications that you select here?
Yeah, you first mentioned like, a logical channel is related to an application, and when you use a logical channel, you can address that application, but then there's also the application identifiers.
So the select command is a standard command, so it supports logical channels in its first byte. You can specify any channel specified in the select command is opened automatically and will be assigned to that application. So if you issue a command to the card, and in that command you will specify a logical channel which was open or not open, it will be logical channel that is available to that application. So any commands sent on that logical channel will go to that same application.
So first you have to open a logical channel, and on that logical channel you have to use the application identifier.
Well, the opening of the logical channel is the same as selecting the application. It is in one command. You can explicitly open a channel, but that's not so useful. But the main thing is you select and you create a logical channel which links that logical channel to the application selected in the card. So any commands on that logical channel will go to that application. So if you do another select, Then you have, with another logical channel, you have two applications on two channels, which can be different applications or can be the same.
Okay, thanks.
Okay. This was the part about talking to cards, where you need protocols, you need to select the application and use logical channels. Let's conclude with some looking at the security. As always, security starts with you, with the designer, the implementer. If you screw up, things won't be secure. It's always important to notice, even many may realize it. Java helps you in doing the right things. It is a bit easier to do the right thing than to do the wrong things. Our intention was that it would be very easy to do the right things and very hard to do wrong things by using much more objects. But we have object-oriented programming, which allows you to encapsulate secrets, encapsulate data, and in doing so you can define your access rules as methods and other ways. So you can actually design and implement and visually inspect your code as being supporting your security rules. The runtime of the card helps you. There is an API for keys, for lots of keys, to building keys, to generating keys, to setting the data of keys. That will help you there. And there is the firewall. We'll make sure that nobody else will tamper with your data. So the only one who can screw up with your data is yourself. And then, of course, there is the firmware in the card, and the hardware, which makes sure that any keys you use, any encryption you, any decryption you will be hard to analyze as DPA. It will be hard to read the keys from memory by breaking into the silicon, etc. So security is really multiple layers, and it starts with you. The Java is only one small element in it, but Java's awareness, object-orientedness, and the framework help you. Objects in Java, keys are objects. There's a whole range of keys that for all different algorithms. So if you create a key, you create a key for a specific algorithm, and it can only be used for that algorithm. You can specify the key as being modifiable by the outside by setting the byte value in it. You can generate it in random in the card. But if you want to accept data from the outside, you can specify encryption to be used on reading, or you want to export a key, you can actually specify encryption to be used for exporting. And I have a bit of Java code here that should show this, if I can find the light here. There is a package called Java Card X Crypto. It's called Java Card X because of export regulations. It was considered better to put the cryptographic package in a separate extension domain. Nowadays things are a bit simpler. There's an example class which uses an AES key. It has a key defined. This is the special type for AES keys. It calls the key builder function to build a key, and the parameters disappeared here for some reason. But you specify the algorithm type, and you specify that you want to use key encryption. And here you see that there is some cipher defined somewhere else in this class, which decrypts or encrypts. You can do both, or either one, the right size of the data for keys, and it's bound to that key. And whenever you want to set some key, so if there is a command, an update command implemented by this method here, where you give it an array of some encrypted key data, you can make sure the key is empty, and then you can just dump the data in the key and it will be decrypted for you. So this makes it easy to do the right thing and manage your key data without exporting or importing it in an encrypted version. Any questions on this? Then we can move on. Security is always relative to what can go wrong. Hardware attacks are known, are mounted to cards. The good thing is there are none that really are relevant to Java cards. Some attacks have been claimed in the world, especially with Light, about attacking Java VMs. But since the VM is not a Java VM, those attacks are not really applicable. All the attacks known to Java cards are basically attacks on the card itself and not on the Java-specific elements in it. The runtime implementation, of course, can be buggy, and over time it has improved, and some weaknesses have been found, buffer overruns and other places. But the nice thing about runtime problems in Java card is the only attacker is someone who has been allowed into the card. So unless you have a card which is completely open and you allow everybody in, your attacker is already known as one of the other applications. And since there are very few multi-application cards in the world where one application is run by one organization, another application by others, those two applications are usually not are usually friendly and never really in an attacking mode. But the weaknesses have been found and have been corrected. And so Java Card, as of now, has no known weaknesses, although they may still be, they'll still exist, of course, like every software. In smart cards and in other places, security evaluation is a very important aspect of making sure that what you talk about, what you build, is really meets some expectations. Common criteria has been involved over the years as a way of expressing expectations about security. What is secure and when do you know something is secure? And it's been applied to smart cards in general and especially to Java cards. Common criteria exists of three big documents describing procedures and terminology for describing security and threats and counteractions and all those things. It also describes how to establish that the product you make are actually meeting the expectations you formulate in that in those description of security. They recognize 7 levels. The lowest level means no security, no statement. The highest level is very few products reach that, and it is very strict, and you have to do a whole lot of formal proofs about the correctness of your design and your implementation documentation, etc. It's based on independent evaluators, organizations which you pay lots of money to read through the stacks of documentation. It probably is around 1,000 pages for a smart card and documentation that you have to deliver. And it's very expensive. The typical smart card product, and you have to do the whole product from hardware to the software and some of the applications, will cost you over 2 million euros to get it evaluated at a reasonable level. Reasonable levels nowadays for smart cards are 4 and over. There's one smart card product at 7, but I don't know whether anybody's actually using it. But it's cool that someone actually achieved it after 10 years of hard work. All in all, there are 50 products you can buy which have been evaluated to a certain level. EAL means it's a level of assurance, meaning how sure can you be that security has been achieved, and those products meet some criteria. Of course, this is very flexible, so you can write very weak assumptions, very weak requirements, and then be proven to meet those very weak requirements in a very strong manner. But the more you go up, in 4 or 5, there are more requirements to actually be some security. So those products, you have some expectation that it is pretty hard to break in. And like all security, break-in in cars is always possible. You cannot expect that any car system, if you have enough value on it, will remain unbroken. So, but a particular card, you will not be able to get in very easily. This is then the end of my main part of the talk, and we can go into some conclusions. Smart cards are very widely used to do something with security. Java cards allow you to do something a bit easier, and security is hard and remains a thing to be careful about. Then there's time for some questions. So, please go ahead. There's a question in the back.
Thank you, Eduard, for this presentation. Please, questions?
Thanks. I was wondering, you mentioned that the Java cards have the ability to generate keys. What entry sources do they use for the random number generators, and is that specified by the Java card standard so that you know when you're writing some code to run in a Java card, you're going to have strong keys generated?
The Java card specifications do not involve any specification about keys or algorithms. Most Java cards nowadays use hardware random number generators of some type. I'm not sure what they use. It may be noise, so you may have an attack on the random number generation by cooling it. But there's hardware number generators. Most countries have standardization bodies that specify cryptographic parameters, like the length of the RSA key that to be used for certain functions. They also specify the quality of random number generators. And most products specified, when they are evaluated, are actually specifying the strength of the random number generator in their security specification. So while the Java card doesn't specify it, all products on the market will meet some government body's expectation of random number quality.
Well, thank you. If I would like to get some hands-on experience with Java cards, you mentioned that they're not freely available. Can I buy them somewhere on a website, or how does that work?
If you go to a manufacturer's website, Giesecke & Devrient or Gemalto are the larger ones, you will be able to buy, they're very expensive relatively, I mean a couple of €100. You will be able to buy a development kit which will come with cards that you can load them onto. The easiest way to work with it is using Eclipse or NetBeans, or there's another framework from University of Michigan where you can actually run the code and emulate it. So the emulation is and they're true complete Java card emulations. So you can actually run it in a true sense, talking APDUs and using the whole stack if you want. But real cards you have to buy from manufacturers. I don't know any source which builds Java cards which are freely available for use. But there may be. I mean, I haven't looked at it very carefully, so there's a question there.
I saw that there was an AIS implementation. Is it in source, and how fast is it?
Again, Java card has doesn't specify anything. It specifies identifiers and data type to...
Yeah, but I saw you use a library.
Well, the library is provided by the smart card manufacturer. And okay. they either use a software or a hardware implementation. And most have hardware accelerators for AES. Okay. And I don't know. You have to look at the product sheet of each of those chips and see how fast they are.
Okay.
And I mean, you can go to Infineon website and look at the products for smart cards, and they will specify the AES implementation they support. STMicron is the same. So those chip manufacturers will actually have done all the work and make sure that they provide the firmware and the hardware for doing encryption. So I don't have no details.
Is there an open source tool chain to work with Java cards, or do I always have to use some proprietary tool chain or middleware?
There is an open source available. Well, both NetBeans and Eclipse come with modules to work with Java cards, including the emulators of the card level. The moment you want to use real cards, you have to go use a real card loader application, which is embedded in a real card. And that usually comes either with a set of open keys that are public. I mean, they are desk keys, and you know the key, and that's published on the documentation. To get those things, you have to go to the manufacturer. So it's open until you need real hardware cards that you want to work with.
Any more questions? Yes?
Hi. Can you return to the slide where you mentioned some evaluation of security levels, some EAL? Yes, evaluation assurance level. Yes. Can you talk a little bit more about that? I mean, what are the kinds of attack and the countermeasure of that?
So in common criteria, you are required to produce several documentation on any product you make. One of those documents is the highest level document, is called the security target. The security target specifies all the threats that your product will counter. It will describe the product, all the interfaces it has, all the types of users, the type of administrating users, and it has to describe the threats that the environment poses and the security that it assumes in the environment, and then it specifies the functions, what that product makes to counter those threats. That is the high-level description of the security that is being provided by a product. That document is formalized. It uses standard phrases taken from the common criteria documentation. It says intrusion detect hardware. There's whole lists of things categorized in families, and this is a pretty complex document which allows you to basically create a specification by using preset phrases and select the specifics for your product in there. That document is the base document that has to be evaluated and seen being consistent with the rules and consistent internally with itself. Then you have a high-level design, a low-level design, implementation design, and etc., etc. So all those documents have to be made and be consistent between themselves, being the proper refinement, and the independent evaluator will evaluate that. The detail in which he goes, the things you need to specify about the threats and measures are specified at the level definition. So an EL4 definition has to include certain countermeasures against certain threats. If you go for 5, you have more threats to counter, more things to work on. If you go 2 or 3, the number of threats is much lower. Also, the process to achieve level 4 is more rigorous than the process to achieve level 2. So the whole common criteria is about doing your utmost best to make sure that what you build is secure. Of course, the testing is done not completely exhaustive. Some intrusion testing is actually done by the testers when they evaluate the product after reviewing the documentation. But they only use it, not full intrusion, they just test some things. And they assume that then they test the same as documentation. I worked on documentation myself based on an old version. When I see the old version being accepted, I say, well, I'm not sure whether I should have accepted that, being ambiguous as it is. But that's how it works. So the next version is better, and another version gets better. So over time, products get better. Specifications get improved. The product actually implementation improves. So you introduce new bugs, but you also remove old ones. So this is it is a process. Security is a process. You will never, when you stand still and you keep the product alive for a long time, you get the MIFARE Classic problem, and after 10 years, you're broken.
Okay, thank you. Just one more question. Do you know how JavaCats are adopted in banking solution? I mean, online authentication in the banks?
I didn't get your question completely.
I mean, how JavaCats are adopted in banking solutions?
I don't understand what you want to know.
Well, maybe later.
Okay.
Any more questions? Well, if there are no more questions, I take the liberty to ask one myself. I know it's rare, but it's sometimes possible that the Java virtual machine crashes. Is that possible at all in this technology? And if so, how do you handle that? And if a card has been crashed, can you throw it away, or is it? How does it work?
So the interesting thing about Java card is that the VM never stops. If it were to die or crash, the card will just reset, or it will get mute, and you have to remove it and reset it yourself. But if you reset the card, it will basically get back into a stable state. The transactional memory guarantees you that the state you get into is something that makes sense. All RAM is of course wiped out after a reset, and the state you want to work with is in non-volatile memory. So you go back to you roll back your whole state to something that is safe. So even if the VM actually crashes, it will do so. There were some security exceptions thrown by the hardware when it detects some key tampering. It will throw the card into mute, and usually when you remove the card and reset it, it will go back and do things again. So this has, so they crash. They can crash because of attacks. They can crash because of software failures, but they can recover because the state is always in non-volatile memory, and that state is a transaction state, so it is actually consistent and usable again.
Yeah, thank you. Well, if there are no more questions, I would like to thank the speaker for his presentation. Don't leave, because I have few now.